right, let's start and begin with a presentation from a scientist, Dr. Annika Svanbäck from the Baltic Sea Center at Stockholm University. And Mrs. Svanbäck will be giving us a fact background about the situation. The floor is yours.
Thank you very much. So I'm going to give a brief overview about eutrophication and the Baltic Sea, describe some of the consequences of eutrophication and some solutions for reducing nutrient inputs. Here we have the Baltic Sea. Eutrophication is a large problem in the Baltic Sea. It is a major threat to biodiversity and ecosystem functioning. And the things we add to the sea generally stays there for a long time because of the low water exchange with the North Sea. And a lot of nutrients have been added to the sea for decades, mainly from sewage, agriculture, and industry. And this have effects in the sea, such as algal blooms, reduced cod reproduction, changed species composition, and oxygen-free dead bottoms. And it affects our possibilities of using the sea and enjoying the sea. So eutrophication is a big problem. But I also want to highlight that we see improvements in parts of the sea as a consequence of reduced nutrient inputs during the last couple of decades. The Baltic Sea can look like this. This is a Finnish coastal area. There's lots of life and beauty in the Baltic Sea that we can also benefit from. And we're starting to see signs of recovery in the sea. And this is great, but we're not done. We need to make further reductions in nutrient inputs to the sea to see more improvements. And this is also required in the Baltic Sea Action Plan, as well as in the Sustainable Development Goals and EU directives. So now I will talk more about the sources of new nutrient inputs to the sea, and that there are opportunities to reduce inputs from land further. And for example, inputs from sewage have been reduced substantially, but there is still work to be done. The EU Court of Auditors pointed out that the Urban Wastewater Treatment Directive is not fulfilled by all the countries around the Baltic Sea, and HELCOM has even stricter limits, requirements for nutrient removal from wastewater. So let's take a look at nutrient flows in the countries around the Baltic Sea. And the box here represents the catchment, the area that drains to the Baltic Sea, the area where the rivers end up in the Baltic Sea. And the width of the arrows represents the size of the nutrient flows. So nutrients are imported to the catchment with fertilizers and feed, and the catchment, the region, is a net exporter of food products. And a small proportion of the nutrient reaches the Baltic Sea, but this small proportion has a very big impact on the sea. So what's going on inside the catchment? Most of the anthropogenic nutrient flows in the catchment are connected to food, production and consumption of food, including what happens with the food after we've eaten it. And fertilizers are used in crop production. We eat some of the crops. 70% of the crops in the catchment is used to feed animals, together with the imported feed. And some of the feed is turned into meat that we eat, and a lot of it becomes manure, which is then used in crop production. And one important issue here is that we have a separation between crop and livestock production. We have areas that are more dominated by livestock production and areas that are more focused on crop production. So in the areas with lots of livestock in relation to the area of agricultural land, feed is imported and the manure is then put on the land close by, and that often results in a surplus of nutrients in that area. And if nutrients were used more efficiently in agriculture and recirculation increased, for example, by using manure more efficiently, we could reduce the import of fertilizers and feed. Another way of looking at this is to map nutrient balances. And here we have phosphorus balances. It is calculated as phosphorus in fertilizer plus phosphorus in manure minus the phosphorus that is taken up and removed with harvested crops. And it is kilos phosphorus per hectares of utilized agricultural area. And where there's green, there's close to balance between phosphorus in manure and mineral fertilizer and what is harvested with crops. And where there's red and orange, there are large surpluses. So here, soil phosphorus may increase and the risk of phosphorus losses increase. And it's also, you could say that it is an inefficient use of resources. And this is a coarse, big-scale approach, but it is consistent for the entire catchment, and it's relevant for the sea. But we should also be aware that there are large variation within each of these little areas. We know that even in a grain area, we have fields where a lot more phosphorus than what is taken up with the crop is applied. So to do measures, we need to go down in a much finer resolution, a much finer scale. And agriculture differs around the catchment as far as growing conditions, climate, the structure of farms, as well as the intensity in crop and livestock production. And these differences are reflected in the different phosphorus use efficiencies we see around the region. And if we would compare this map to a map of livestock density, how many livestock there are per agriculture area, we find that there's larger surpluses where there's lots of livestock in relation to available agriculture area. Because manure is heavy and difficult to transport for long distances, so it can become a problem instead of a valuable resource. And there is opportunity for agricultural systems in the Baltic Sea region to increase nutrient use efficiency and recycle more, for example, by using manure more efficiently and reducing the need for imported mineral fertilizers. So we can work with source factors, reducing the inputs, not putting on more than what the crop need. That's sort of step one. Step two, there's a lot of other things that a farmer can do on his farm to reduce nutrient losses, and that to keep nutrients on the field and to reduce the transport of the nutrients that is lost from the field. And this will often be different measures on different farms, and it requires more site-specific knowledge. It could be things like buffer strips along water courses. Let's see now. And so we see there's surface runoff, here water moving, with lots of phosphorus moving into the stream. And this buffer strip would probably have needed to be a bit wider, where we have the surface runoff. But up on the hill where there's no surface runoff, it could be narrower. So local knowledge can make these measures more efficient. And we also have an example of a phosphorus pond, a phosphorus sedimentation pond that can catch phosphorus. We can use measures like catch crops, cover crops that keep nutrients on the field after the main crop has been harvested. And this manure spreader symbolizes that it is important to fertilize at the right time and using good techniques for spreading manure, etc. So, to summarize, eutrophication is a major threat to biodiversity and ecosystem functioning in the sea, but the sea is not dead. There's lots of life worth protecting, and it can benefit us humans if we have, for example, less algal blooms and more cod. Nutrient inputs to the sea needs to be further reduced. To achieve this. And large nutrient reductions have been made in the past, but we need to do more. There is opportunity to reduce further nutrient inputs from land to sea. And all countries do not meet the requirements for sewage treatment, and there is potential to use nutrients more efficiently in agriculture, thereby reducing nutrient surpluses and the risk of nutrient losses. Thank you.
Thank you, Annika, very much.